Hello and welcome back to another Chemistry the Right Way with me, Mr. Right. Go ahead and make sure you subscribe to this channel and click the like button and do all that. And you can always leave a comment for me if you'd like me to go over anything in particular. Right now I'm just doing a series of 15-minute tutorials in order to help you get through your chemistry studies. There's going to be some videos coming out later on that are much more in-depth. So today's 15-minute tutorial, we're taking a look at oxidation states and periodic numbers and how we can help to understand what's actually going on with this idea of electronic charge, or in other words, why we get the development of anions and cations. So, first thing we're going to do is we're going to take a look at the periodic table of elements, and we're going to take a look at the noble gases. So the noble gases, from lightest down to heaviest, are going to be helium, neon, argon, krypton, xenon, and radon. Okay, now the bit there is if we take a look at their actual atomic number, their atomic number, and the atomic number mirrors the number of electrons that each one of these species actually has. So if I do the nuclide notation, I'm going to go 4 over 2 He, and I'm going to go 20 over 10 neon, just consulting the periodic table just to make sure I'm correct. I'm going to go 40 over 18 for argon, and then I'm going to go 83 over 36, xenon 131 over 54, and then lastly radon, I'm going to go 222's most stable radionuclide over 86. So let's take a look at just those periodic numbers, just those atomic numbers: 2, 10, 18, 36, 54, 86. These are really important to us. I'm going to start off with the number 2, then 10, then 18, 36, 54, and then 86. Now, again, you understand where these numbers come from. These are the numbers of protons in each one of these nuclei, which means that they're the number of electrons that I need to have in order to balance out those positive charges. So this is 2 positives, so I need 2 negatives, 10 positives, so I need 10 negatives, etc., all the way down the line. What I'm going to do now is I'm going to take a simple number line and I'm going to take a look at the differences in those atomic numbers. Okay, so I'm going to start at 0, and then from 0 to 2, the difference is 2. From 2 to 10, the difference is 8. From 10 to 18, the difference is 8, right? As in 18 minus 10 is 8. 36 minus 18 is 18. 54 minus 36, 54, 36, another 18. 54 to 86 is 32. These numbers are effectively what we'd consider to be the electron shell numbers. So I'm just going to sort of show you what I mean by that. When we're building atoms, we start off with that tiny little nucleus, we put all our positives, we have to throw in some neutrals, those neutrons, in order to stick the nucleus together, and then to balance out that positive charge, I have to go ahead and have to coat it with negative charge, those electrons that orbit on the outside. So why do we have them? Well, we have these shells. So if we have, for instance, an atom of, we'll go ahead and we'll just take a look at element number 36, that's going to be krypton. Krypton's atomic number, 36, means that there's 36 electrons balanced out, but they're not just built in a simple sort of straightforward manner, they're layered on. Now a lot of people go ahead and think about electron layers as being distance layers. They're not. They're actually just energy layers. it's quite difficult to wrap your mind around. It's not that they're layers like layers of an onion, that's a physical separation distance. They're layers in terms of how much energy they have in their resting states. And that's not really a matter of energy in terms of kinetic energy, like how fast they're moving. It's something a little bit more complicated called the energy state of the electron. But let's just take a look at this one. So krypton has got 36 electrons, and we're going to fill up these layers using these difference numbers. So in the first layer of any atom, the first energy layer, you can only fit 2 electrons. So there's 2 in that first layer, then there's 8 in the next layer. 2 plus 8 is 10. I can fit 8 in the next layer. Okay. 2, 8, 10, 18. And then after that, I can fit 18 in the next layer. And 18 and 18 is 36. And that is an atom of krypton. And we can do that for all of the noble gases. And what we'll find is these are the perfectly full energy states of all of the electrons. So we're going to use this pattern and this idea, and we're going to take a look at just some other random elements, right? So just off the top of my head, I'm going to choose magnesium and sulfur. Just off the top of my head, purely. Magnesium, Mg, I think we're at a mass of 24 over 12. Yeah, we are, there we go. 24 over 12. And I said sulfur, that's going to be 16 over 8, 32 over 16, excuse me. Okay, so I'm going to do that same layering effect. I've got 12 electrons to put in. Well, start layering in those energies. So I've got 2 in that first layer, and then I can fit 8 in the next layer. So remember, those numbers are, these called the periodic numbers, right? 2, 8, 8, 18, 18, and 32. 2 and 8 is 10, and now I've only got 2 plus 8 is 10, and I've got another 2 left in that third layer. Okay, going to do the same for sulfur. Sulfur can fit 16, so 2 in the first layer, 8 in the next layer, that gives me 10 electrons. And then I can fit 2, 8, 2 plus 8 is 10, I can fit another 8. I don't have 8, I only have 6. Okay, so I'm just going to kind of leave us with this, right? I can fit in this layer, right? 2 in the first, 8 in the second, 8 in the second. I can fit 8 there, and I can also fit 8 there. Well, this is the idea how oxidation states come about, why we have anions and cations, and why they stick together, why they form. First of all, we're going to go ahead and we're going to call every energy level that's full, every single one of those, these guys and these guys are what we call core electrons. And then the ones beyond the core, we're going to call valence electrons. Now, the actual valence electrons and the core electrons are arranged in sort of sub-layers within each one of these layers. So this is a basic piece, but stick with me, bear with me on this bit. In my valence shell for sulfur, I can fit 8. I've got 6. For magnesium, I can fit 8. I've got 2. And so the question becomes, is it easier to empty your valence shell or to fill your valence shell? So here, for magnesium, because I have 2, I can either get rid of those 2 outer electrons, just get rid of them somehow, or I can gain 6. So it's a matter of lose 2 or gain 6. Here, it's the reciprocal of that, right? I've got 6, I can either gain 2 or I can lose 6. Every time I gain, every time I lose, it's kind of like an energy penalty. So it's much easier to lose 2 than it is to gain 6. It's much easier to gain 2 than it is to lose 6. And the ultimate piece is this. Whenever we fill up these electron layers, we calm down the entire, what we call internal energy of the atom itself. So the atom itself becomes much more stable, much less reactive. So you can see obviously what's going to take place here. Without affecting or influencing the core electrons, without influencing that, right? I'm going to play around like a little jigsaw puzzle with my valence electrons, excuse me. And atoms are doing this without our help all the time. So simple, right? If I get rid of these 2 and I accept those 2, I'm going to end up like this. 24 over 12 mg 2, 8, and that's it. If I go down to here, 32 over 16 sulfur. Remember the symbol and the atomic number are always linked. Okay, I'm going to end up with 2, 8, 6 plus 2 is another 8. Take a look at that. Magnesium, 2, 8, 2, 8. Those are my periodic numbers. Those are my numbers of stability. Take a look at sulfur, 288, 288. Again, the periodic numbers of the noble gases, the very stable elements. But let's just count up. I have 12 positives in the center, 12p plus, right? And now I've only got 2 plus 8, 10 e negs. 12 positives, 10 negatives, equals an overall charge of 2 plus, or as we'd say, plus 2. Right? I go down here to the sulfur, I do the same thing. I've got 16 positives, 16 protons, and 2 plus 8 is 18 negatives. 16 positives plus 18 negatives equals 2 extra negatives. So this has got a charge of -2. So now what I've done by exchanging those valence electrons, those outermost electrons, is I've created ions. And in this case, wonderfully, I've created a magnesium cation and a sulfur anion. Anions and cations mutually attract each other. So I've just generated my first chemical formula, right? I've got myself, we just write it positives and negatives. I've got an Mg of +2, and I've got an S at -2. And those charges balance perfectly. So I've just created the compound magnesium 2 sulfide. The 2 with the cation refers to how big the cationic charge is, and the "ide" just means an anion. Unfortunately, you don't know the actual charge, you have to work that bit out. But that's how it all works, all across the periodic table. Sometimes they balance out nicely, +2, -2. Sometimes it's a little more complicated, like you have to have 2 hydrogens to balance 1 oxygen in order to get all of the anions and the cations to transfer correctly. And just a quick note on hydrogen itself, right? You'll remember at the very, or I hope you'll remember at the very start of the video, I started out with a 0. I said 0, and then the difference between 0 and 2 is 2, the difference between 10 and 2 is 8, 18 and 10 is another 8, so we have this mysterious 0. We don't use it a lot, but it's ridiculously important. Or in other words, hydrogen has got one valence electron, 1 over 1. So it's only got the 1, right? And that makes it kind of unique because it's equal in distance to go to the second, to gaining an electron, or to losing an electron and having zero electrons in that energy shell. And so that produces us with hydrogen positive ions and hydrogen negative ions. Surprisingly enough, one is actually more common than the other. It turns out that this is actually more stable in most cases than this. This hydrogen 1 ion is just more stable in more cases than what we call the hydride ion, but we do occasionally see that. Thank you very much for watching. I hope that helps explain to you. And last note about those periodic numbers, the cool thing is if you take a look at any family of elements on the periodic table, any family of elements, doesn't matter what the atomic number is, the element above it or below it is always one of those periodic numbers away. Makes no difference if it's element number 50, right? That's going to be close to this 54 right here. There's going to be elements either at 82 or at 50, 50 plus 32 is 82, right? So there's going to be an element in the same family at 82, and then go ahead and subtract 18, and there's going to be another element there at 32, right? Thanks very much for downloading. Again, please click like, subscribe, do all that stuff. And if you have any special topics that you would like for me to cover outside of these 15-minute tutorials or even within it, go ahead and leave me a comment. Thank you very much. Enjoy the rest of your day. Bye.